whens, ifs, or buts. What numbers did we do? 8 through 30, maybe. Maybe. That doesn't make any sense. That's what you wrote down? Is that what you're telling me? All right, that's good enough. Good enough. Y'all have to thank Joe. He's coming in clutch. Okay. All right. Unit 8, Lesson 1, Geometric Mean. All right, number 8 is 18. 10 is 10 times the square root of 5, which is approximately equal to 22.4. 12 is 12 times the square root of 5 over 5, which is approximately equal to 5.4. Number 14, excuse me. Triangle MNO is similar to triangle NLO is similar to triangle MLN. 16. Triangle QRS is similar to triangle RTS is similar to triangle QTR. 18. X equals 6. Y equals 3 times the square root of 13, which is approximately equal to 10.8. Z is 2 times the square root of 13, which is approximately equal to 7.2. 20. Excuse me. X is 2 times the square root of 10, which is approximately equal to 6.3. Y equals 2 times the square root of 6, which is approximately equal to 4.9. Z equals 2 times the square root of 5, which is approximately equal to 7.7. I should say that if you have the reduced square root or the decimal equivalent, either one is correct, although I would argue strongly that the reduced square root is the better answer if you only have one. Okay. 22, x equals 40. Y equals 10 times the square root of 5, which is about 4. Z, 20 times the square root of 5, which is approximately 44.7. 24 is 18 feet. 26 is 2 times the square root of 3, or 3.5. 28 is 5 times the square root of 3 over 4, which is about 2.2. Number 30, x is 2 times the square root of 5, which is approximately equal to 4.5. Y is equals 2 times the square root of 5 over 3, which is approximately equal to 1.5. And z is square root of 2 over 3, which is approximately equal to 0.5. I will take questions, but I'm going to start warning you about something. It's not from this lesson, so don't stress too hard. But there is a lesson in this unit. It's lesson 3, in case you're curious, where on the test there will be a no calculator portion, which will be shorter than the pre-cal version of the same thing. But there will be a portion on the test where you have to know the things in here without the buttons. You got this. I've got a real easy way for you to memorize what you need to memorize. And if you'll listen to me, unlike the kid in pre-cal who still keeps printing out his stupid thing that's forever and horrible to memorize, if he would just listen to what I'm telling him, he can memorize it like that. But you know, whatever, it's fine. That's fine. Sometimes people don't want to listen. It's okay. What questions do we have on this lesson? What? 22. Okay. Kill the proof. Make it die. Even if it's a really short proof. Okay, 22, he says. We got a triangle. And it looks more or less like this. With this is a right angle, this is a right angle. This is 20 z x 10 y. So, what do we do? Yep. And then after we stare at it, what do we do then? What if you go back to your notes, if you go back to the lesson, which tools in our tool belt are useful to us? There's actually multiple ones, but there is one that is shorter, a shorter chunk. That's okay. I don't care either. No. The 8.2 theorem, or maybe even the 8.3 theorem. Those are probably great ideas. Those are probably wonderful ideas. Let's put those up on the board. If you don't have these in your notes from the lesson, you should probably add them. These are two theorems that have to do with the geometric mean. The geometric mean, this lesson, is the most geometry part of this unit. Excuse me. Everything else kind of jumps fully into trig. What is that terribleness? Somebody do it drilling something or something probably across the street. That's horrific. I hate it. Okay, so what does it say? Well, I drew the picture for the top one. We've got some proportionality happening, right? It says that x to h, so the little bitty one on the little bitty triangle, all these triangles are all proportional, every single one of them. We get that earlier in the lesson, right? They're all proportional, which is why this theorem works, because this triangle is proportional to this triangle is proportional to that triangle, all of them, right? It's the answer to one of the earlier problems in the lesson. So x to h equals h to y. That's because if we extracted this triangle and pull it out, the h is now the little leg of this medium-sized triangle, right? That's why this works. Now, you could also flip this entirely the other way around, right? Doesn't matter as long as the h is flipped on both, because this would be the same proportion as h to x equals y to h, right? Same. Doesn't matter as long as you flip it. As long as the h is on top of one and on the bottom of the other, right? That's all we really care too much about, right? So that's how it works. Now, if we take, and this is also useful, now you can set it up like we're doing this problem, and I haven't even looked to see whether we're using this one or the other one or both, probably both. Excuse me. If we take and we solve this somewhat, we can get something simpler, or sort of simpler, right? Because if we do a cross multiply, we get h times h. What is h times h? No, it would be h plus h, but that's a common accidental mistake. H times h isn't 2h. What is it? H squared. True enough. There's a 2 involved, just in a different place. And then x times y is just x times y. Then we continue solving for h, we take the square root of both sides. And we end up with h equals plus or minus the square root of x times y. However, we are talking about distance here, so unless you're doing this for like physics or something, then you might be talking about displacement. But since we're talking about distance in this class primarily, it's just h equals the square root of x times y, which should be really familiar. Should be the geometric mean is where it comes from, right? It's kind of making sense. So when you're asked how to find the geometric mean between two numbers, this is what you're doing, right? This is where it comes from here. And then the other theorem that kind of goes with it is the one that relates the legs. So we have the same picture. We got a right triangle with an altitude drawn right there. If you remember back from our segments of triangles, an altitude goes from the vertex and is perpendicular to the other side, right? So that's the shape. And then we've got other things, and they label them slightly different for convenience. They label this as A, B, and C, which makes sense because C is the one that goes with the right angle because it's crossing the hypotenuse of the big triangle. And then they label the side, they also label this as a D because we need one more point. So this is, they label that as B or D, let's see. B, yeah. That's what I figured. Label this is B and this is A. And then the longs, this is X and this is Y. They abandoned their naming convention, which is fine. I probably would have done the same. This is length of C, right? So how do these proportions work? With the legs. I did talk about this in the video like years ago, right? Or did I not? Did that happen in the notes video or no? Did it happen in the video, yes or no? Do you have this in your notes? Okay, good, good. I'm glad I'm not just like teaching brand new. That happens a couple of times, I think in Algebra 1, where past me, for some reason, left stuff out. Eventually I'll redo all of the videos and I've got some better systems for doing them now and whatever else, but eventually it's not today. That's true, unless I do, because even if I go get a job at public school, which is a possibility right now, don't know what's going to happen, but if I do that, I probably will still keep making videos, probably, but we shall see. But I will have to do them on my own time because I don't want whatever school I work for, if I do that, to own them. I want me to own them. So, it's the long side, right? Right? The long side of C in this case to A. The long side, it's always a long side in this the leg proportion to A equals, and it's the one that goes with A, right? So it equals A to Y. Is that right? Is that right? What am I doing? Yeah, good. I am right. I'm happy. I psyched myself out for a second. So the leg is the one that stays the mean, right? And then the other two, and so it's the one that gets flipped back and forth. And then we solve it the same way, so I won't belabor that, right? We did it in the video. So A would equal the square root of C times Y. And then you can do the same proportion, but with the B and X side, right? So B equals the square root of C times X. So we come over here. This triangle is topsy-turvy. He's flipped and flopped. So on the H and the Y, we've got a number for the altitude, right? Good. So translating back to these, H equals 20. Right? And on that one, we're interested in the little bits down here, right? So x is x, I suppose. So x to 20 equals, and the altitude is the one that gets duplicated, opposite, right? So 20 over 10. Does this make sense? Good. He's solvable now. He's just a simple proportion. We did that a bunch last unit. What's 10 times x? 10x. What's 20 times 20? What? It is 20 squared. That is true. Good connection. But let's actually evaluate that. What is 20 squared, or 20 times 20? What's 2 times 2? Yeah, I don't think you needed that calculator, bro. You got this. Now what? Divide by 10, and we get x equals 40. True enough. Makes sense, doth it make, or not so much? Good. What number were we even doing? 22? Yeah. Great. So that's one of the three puzzle pieces. So we have that this equals 40. So now we need to get to these guys, which might be a little bit more tricksy, but not really. So we were using this one, but we can't use that one anymore because this one doesn't have to say anything about the legs of the big triangle, right? So we got to use this one now. We got to have the big chunk here. So we don't yet have the big chunk. How do we get the big chunk? Technically, yes, but like, what are we actually doing? We've got to do a little math. 10 plus x, and x is 40, so it's 50. So with these letters, C equals 50. So we're going to have some sort of fraction with a 50 here. I was about to lie. Just kidding. I always want to, for whatever reason, on this geometric mean, I always want to have the big one be the one that crosses, but it's not. It's the legs. Which is why the name might be useful. If you remember, it's the geometric mean leg theorem or something like that. Maybe it'll help you remember that the leg is the one that gets duplicated. So, what proportion would we write for y? There's two ways we could write it. What's one of them? What? 10 times 50 square rooted. True enough. If we go for the solved one. What's 10 times 50? 500. True enough. Now, we need to simplify that square root. I would like us to practice at least briefly. Now, your calculator will do this. This is not on the no calculator portion. Your calculator will do this for you, except maybe that calculator. I can't remember whether it'll give you an exact value on a square root or not. I don't know. We'd have to check it. Okay, so in order to simplify this, now you'll have to really do this like for real, and you can use a calculator to kind of help you get there in Algebra 2. But in Algebra 2, you got to be able to do it by hand. So to do it by hand, we need to know what perfect squares go into that. So it's useful to know what are perfect squares. What does that mean? Yeah, so let's list a few. 2 isn't 1. Neither is 8. 4 is 1 because 2 times 2 is 4. What's 3 times 3? Times. What is 4 times 4? 4 times 4. 5 times 5. 25. What's the next one? 36. What's the next one? True enough, 49. What's the next one? 64. That's plenty for now. There's a whole heap of them. There's infinitely many of them, continuing to get larger and larger. So do any of these go into 500? One of them kind of obviously does, if you think about money. So 25 times what equals 500? So do 500 divided by 25 enter. Or you could think in money and you got this. Because 4 quarters make $1, we got $5. So what's 4 times 5? Somebody give me an answer. We got this. 20 sounds great. So we can split this into the square root of 25 times the square root of 20. What's the square root of 25? You don't need a calculator. What times itself once gives you 25? 5, true enough. Now, on this one, are there any perfect squares inside of 20? Do any of these go into 20? 4 does, true enough. 4 times what? 4 times 5, so square root of 4 times the square root of 5. What's the square root of 4? Thank you. What's 5 times 2? It is 10. True enough. You could also show, at any point in this thing, you could show in your calculator and get approximately whatever the heck it is. Who the heck cares? So because you need to learn the skill to be able to do it. And you need to learn how to, and this is one, okay, so actually when I first started teaching math, I would throw this out. But as I've taught longer, I realize some of my students will go to college. Now, some professors aren't going to care if you simplify your radicals, and some will. Would you like to know why we even square our radicals in the first, simplify our radicals in the first place when we have calculators? I'm going to tell you. Are you ready? So there was a time when calculators didn't exist. I know that's scary, dark ages, but it happened. There was a time before calculators. And whenever you would do square roots, before you had calculators and you use a slide rule or whatever you use to do big maths and all the things, or just your head, there was a table that would be in the back of your book that would have square roots approximately equal to this decimal. Like this one would be equal to 2 point whatever it is, right? Yeah, great, that. Yeah, 2.4 something, I don't know, whatever. And so you would, but it wouldn't have the square root of 500 on the table. So you have to go down to the simplest one, and then you have to look it up on the table and be like, okay, it's this, and then you shove it in there. That's why this skill even exists. This skill is useless in 2026. Absolutely useless. However, there are some professors that are going to make you do it, so I keep it in here. Why do you do it by hand? Because I want you to be able to do it. Know the skill. It's not even that difficult because you just have to know these things. If it was hard, then I'd probably still check it out. That sort of answers your question and sort of doesn't. But that is the justification I have for it. You can decide whether you think it's a good justification or a stupid one. That's fine. I'm still going to make you do it. So there it is. There aren't very many things like that in what I teach and how I teach, but there are one or two. This one, really there are two that I can think of off the top of my head that I teach because you might need it later in your life. And that's this and complex numbers. They're kind of like not really that helpful to most people. But complex numbers are kind of cool because 2 dimensions are cool. So, we do the same thing to get z, right? Same as this, but with 40 and what am I saying? Oh, and 50, yeah. So we put a 40 here and you get the same answer. What are the questions from this lesson? 30. And I know that the meme and the true fact goes around that high school teachers are like, how are you good to do the things? You got to do the things and the things. And then in college, the guy comes in and flip-flops and he's like, I don't care. You can show up if you want to show up, whatever. I know that sometimes exists. And there are some math professors that are going to care. They're not all like that. But 30, here we come. Look, it's got square roots. Got square root of 2. 3 times the square root of 2. Oh, this is a special right triangle, which y'all don't know what that means yet. Z and Y. And we got to find the things. We're gonna keep this one not decimals for practice for later because square root of 2 and 3 times the square root of 2 are things that are going to show up on the no calculator portion. So we're going to practice early dealing with them. So, what relates to what, where, and why? So 3 to the square root of 2 to the square root of 2 equals what? No. Let's use the altitude one, right? Because you start with the square root of 2, which is a good idea. Either accidentally or on purpose, you picked exactly the right place to start. So the altitude goes, so we've got the little legs, the altitude, and then what's going to be over here? Which one duplicates? The square root of 2. That's true. And the duplicate one is on the opposite side. So the altitude is up over here. And then what's going to be down here? Z. Z is correct. Okay. So we've got a proportion. This, what we're about to do is going to look a little scary, but I promise you it's easy. And so if you'll let me and you won't shut your brain off, it's going to be as easy as it is. Okay, so how do we solve a proportion? Cross multiply. True enough. What's 3 times the square root of 2 times z? 3 square root of 2z. True enough. Although we usually put the z on the outside, that way the radical's at the end. Just so it doesn't look like we have other stuff. But it's not wrong to put z at the end as long as it's not under the square root. Now, this one is easy, but pause for a second. What is the square root of 2 times the square root of 2? What? Is that what you said? I said, what's the square root of 2 times the square root of 2? Yeah, so I'm going to talk about 2 ways. That's true. So when you multiply 2 squares together, you multiply what's inside.
So the square root of 2 times the square root of 2 is the square root of 4, right? That's true. Now, square root of 2 is the same as the square root of 2, right? So, like you said earlier with the other one, it's also the square root of 2 squared, right? Because they're the same. If you have x times x, it's x squared, right? Now, this is going to give us some intuition for what's going to happen here in a minute. What's the square root of 4? That's 4 squared. What's the square root of 4? That's 4 plus 4. What's the square root of 4? What times itself twice is 4? 2. True enough. Bro. Now, what are square root and squared to each other? They're canceling because they're opposites or inverses, right? So they cancel. So that side also equals 2. So the square root of 2 times the square root of 2 is 2. Now what? What's attached to z? What else? The 3. And the square root of 2. True enough. How are they attached? Are they added, subtracted, multiplied, divided, or something else? Not something else. They're not divided. Where's the plus sign? Where's the minus sign? They're right next. When you got a number next to a letter, how are they attached? Multiplication. So we divide to get rid of them, right? So we got z left over here. Now, something's got to happen over here because we don't like square roots in the denominator. And if you ask the same question you asked before a minute ago, about other stuff, the short answer is because we don't. Sorry, I don't have a better answer than that. We don't like square roots in the denominator, so we have to rationalize. Now again, I said this was easy. This is easy. It is easy. We don't got to deal with no conjugate or nothing. Do that in algebra 2. To get rid of a square root of 2 in the denominator, we use this idea. The square root of 2 times the square root of 2 is the square root of 2 squared. So if I multiply this times the square root of 2, the square roots are going to cancel away. But I can't just do that. Because if I just do the square root of 2 in the denominator, then the number is totally different. If I multiply something times a half, that's a totally different number. But if I multiply it times 1, it's the same number. So if I just put the same thing on the top, now that whole blue mess equals 1. I can multiply 1 times anything, and it stays the thing, right? What's 2 times the square root of 2? Not a trick question, just a simple answer. What's 2 times the square root of 2? Oh, that would be true if this one was in the square root. It's even simpler than that. Like in the denominator would be the square root of 4, which we know equals 2, right? So down here it's going to be 2. But 2 times the square root of 2 is 2 times the square root of 2. And then the denominator, we got the 3, and then square root of 2 times the square root of 2, we already figured out equals what? I don't know what happened, but Disney ruined it. Okay, what does the square root of 2 times the square root of 2 equal? I so want to know what they're talking about, but it's also Jameson, and so I don't want to ask him because he'll talk to me for an hour and a half about it. So What does the square root of 2 times the square root of 2 equal? I didn't know I was going to be pulling teeth so much today. It does equal the square root of 4. What does the square root of 4 equal? 2. So the square root of 2 times the square root of 2 equals 2. So 3 times 2 in the denominator. We can simplify one more bit, or 2 more bits if we go the long way around. What can we do? We can, because it's times. If it was plus, we couldn't, right? We can cancel out the 2's. Or you can multiply 3 times 2, and then you can reduce 2 over 6 to 1/3, and you get the same answer. That would be the long way around. So z equals the square root of 2 over 3. So z equals the square root of 2 over 3. How we do it on time? We got enough time, I think, probably. So we need this whole bit, right, for the next one to get to the y and the x. So we need to do 3 times the square root of 2 plus the square root of 2 over 3. Now, there's a couple things, a couple thoughts here that are potentially, hopefully useful to you. One is you can treat a square root just like a letter, just like a variable. So you can pretend like square root of 2 is just like an x. So you can just combine like terms and leave it in terms of the square root of 2, right? Because if we say x equals square root of 2, then you'd have, well, let's use a different letter. It's not up there. How about a? So we'd have 3a plus a over 3. These are like terms because they both have an a in them, right? So to add fractions, what do we need? Fourth grade math, you got this. In order to add fractions, what do we need? That's how to divide fractions. We do need a common denominator, so we multiply this times 3 over 3, we get 9a over 3 plus a over 3. What's 9/3 plus 1/3? 10/3, true enough. So same idea over here, right? You'd have 9/3 plus 1/3 the square root of 2, so you'd end up having 10 times the square root of 2 over 3. And that's this big chunk over here. That is the C letter from our theorem diagram, right? Then we can do some proportions to solve for x and y, right? Or we can do the square root. We can use the simplified square root one. So what would x equal? It would equal the square root of what? Three times square root of 2 times what? No? It's times the big one, right? Which is this one, right? Times 10 times the square root of 2 over 3. I'm going to simplify this. It's going to be easy. This, you won't see something this ugly looking on the no calculator portion. You will have to rationalize stuff on the no calculator portion. But most of them will be ones that you already know, so you may have memorized the rationalization. So, whatever. No big deal. So, what can we do to simplify this mess? Find the things. I found them. Now what? If I do this, does it help you? See what we do? So we don't have to, because multiplication. right? We could, but we end up reducing it out anyway. We can pre-reduce where? What happens with the 3's? They cancel because of multiplication, right? What does the square root of 2 times the square root of 2 equal? 2. You did it. Good job. We're learning. We're tracking. So we've got square root of 10 times 2. What's 10 times 2? 20. Good job. Square root of 20. Are there any perfect squares inside of 20? Yes. 4. So we have the square root of 4 times the square root of 5. So x equals 2 times the square root of 5. Then we can do the same thing with y, right? Y is the same idea. So y would equal the square root of 2 over 3 times the big one, 10 times the square root of 2 over 3. What do we do with that mess? They don't this time, although they are going to do something cool in a minute, because they're not one on the top and the bottom. What is the square root of 2 times the square root of 2? 4. Not 4. What'd you say? 2. True enough. So this equals the square root of 10 times 2 over 3 times 3 is 9. We already know that the 10 times 2 in here is going to turn into 2 times the square root of 5. When we take the square root of a fraction, we do the square root of the top over the square root of the bottom. So we already know the top one's going to turn into this because we already did it up here. Right, so the top is going to be 2 times the square root of 5. What's the square root of 9? 3. True enough. We did it. So do you agree? Was nothing up here hard? Or do you totally disagree? Wow, that's crazy.
Could you take like 3 times the square root of 2 and make it a decimal before you start?
In geometry, yes. Yes, you can. If you were in Algebra 2 or in Pre-Cal, I might count off a point because that's ugly. But sure, totally fine. You could totally do that. But I do definitely in geometry accept decimal equivalents. Except that little short no calculator portion, but that's just going to be memorized stuff anyway. And it's easy to memorize if you listen. So, no problem. But other than that, yes, you can. Sure. Totally fine.
And the theorem we used, was it for legs?
We used both. So to get to the z, we use the altitude one, right? And then to get x and y, we use the leg one. Does that make sense? Yeah. Okay, good. Okay, kids. See you Thursday. There'll be some Google Classroom stuff up before the day is over. And we'll keep on trucking along.